Hello students, today's our topic for discussion is common base transistor. As we know that on the basis of construction we have two type of transistors. One is NPN type and another is PNP type. In both the transistors, if we give their symbolic representation, there are three terminals. One is emitter terminal, another is base terminal, and the third one is collector terminal. For the biasing of the transistor, we need two terminals on the output side and two terminals on the input side. It means instead of three terminals to bias or to connect the battery or to connect the source, we have to take two terminals on each side, on input side and on output side. To make this circuit or this biasing possible, out of these three terminals, we take one terminal as a common terminal every time. So, as there are three terminals, and if we take one terminal common, it will be in input side as well as in the output side. Then there are three possible configuration on the basis of the terminal which is taken as common. Hence, there are three type of configurations in the transistor for the biasing of the transistor. First is known as common base configuration. It means the base terminal is taken common. It will be in the input side as well as in the output side. For example, in case of NPN transistor, if we have to show the base terminal as a common terminal, we will show it like that. This is our emitter terminal, this is our collector terminal, and we will represent the base terminal on both the sides. It will be in the output side as well also in the input side, and this is our base terminal. So this configuration in which the base is taken on both the sides, input as well as output, or base is taken common in the output as well as input side, that type of configuration is known as common base configuration. Similarly, the second type of configuration is known as common emitter configuration. In common emitter configuration, now we will take the emitter terminal common in both the side, on the input side as well as on the output side. In every case, we are considering the NPN transistor as our arrow is pointing outwards, the outwards to the emitter terminal. It means we are representing our NPN transistor. This terminal is base terminal and this is collector, and in this configuration we are taking the emitter terminal in the output side as well as the emitter terminal in the input side. So this type of configuration is known as common emitter configuration. Similarly, now you can easily represent the common collector configuration. In common collector configuration, now you can easily represent it by your own, that if this is our base terminal, this will be our collector terminal, and the terminal having arrow is our emitter terminal. And now we will take our collector terminal in the output side as well as in the input side. In every type of configuration, we will make the transistor to work in the normal mode or in the active region, where we know that input side should always be forward biased and the output side should always be reverse biased. Hence, in common emitter configuration also, the input side should be forward biased so that the transistor can work as an amplifier or as an oscillator, and the output side should be reverse biased. Similarly, for the third configuration also, the input side should be forward bias and the output side should be reverse biased. Now we will discuss our today's topic, that is common base transistor. In common base transistor, to explain its features, we have to explain its characteristics. Characteristics are the graph between the two physical quantities, and in case of our configurations, we take the third quantity as a constant quantity. Let us now explain what is common base transistor configuration. For this, we have to draw a circuit diagram, and we are taking the again NPN transistor, and the configuration is common base, hence we are taking the base terminal common in the output side as well as in the input side. As we have taken the NPN transistor, the arrow on the emitter terminal should be in the outwards region, pointing should be out in the outward region. This is our collector terminal and this is our base terminal. Now we have to give a connection base in the output as well as in the input side also. To measure the current in the input side, we will connect a ammeter in the series of the ammeter, and this is milliammeter because the current in the ammeter is of order of milliampere. And to find out the voltage in between these two terminals, that is ammeter base terminal, we will make an voltmeter to work in the parallel in between the ammeter and the base terminal. To provide the changing voltage in between these two terminals, now we will set up a rheostat adjustment in this region, and it will be like this. And we know that these two terminals are our input side, and we have to make it in forward biasing. It means the N type terminal, that is ammeter, should be connected with the negative of the battery, and let us consider this voltage source is represented by VEE. VEE is a voltage source providing forward biasing to our input signal, and this voltage source is made variable. Now we can make our voltage 0 volt, 1 volt, 2 volt as we move this key towards the upper part of our rheostat. This voltmeter gives the input voltage, that is the voltage in between the ammeter and base region, and this ammeter gives us the input current, and input current is our ammeter current, and the arrow is showing the direction of the ammeter current. It means the ammeter current is moving outwards from the transistor. This is the direction of ammeter current. If ammeter current is moving away from the transistor, then the base current as well as the collector current will move towards the transistor. According to the Kirchhoff's junction rule, the total current at the junction should be equal to 0. Similarly, on the output side, we have to do our reverse biasing, and to find out the current in the output side, we will put a milliammeter in the series of the collector region, and to find out the output voltage, that is the voltage in between the terminal collector and base, we have to connect a voltage source, and now this voltage source is our VCB. And to give the reverse biasing in the output circuit, we will have a potential divider circuit or a rheostat, so that we can, with the help of a voltage source, give a reverse biasing. As we know that this is NPN transistor, emitter is n-type, base is p-type, and collector is n-type. To make it reverse biased, the collector region is connected with the positive terminal of our source, and let us consider the source. Here we are denoting it with VCC. This is the circuit diagram through which we can easily study the different characteristic of common base transistor. Now, to make it more easy, let us consider the block diagram of this common base transistor configuration. As we know very well, in case of NPN transistor, the emitter is heavily doped with n-type impurity, and there is large number of electrons in the emitter region. In the base region, there are few holes, and it is the lightly doped space in the transistor, and in collector region this is moderately doped region. There are again few electrons here. As this emitter base terminal is the input terminal of our common base configuration, and we have to give it forward biasing, now we will put the battery, and we know that it will be in the forward biasing, and to make it in forward biasing, the p type is connected with the positive and the n type is connected with the negative, and this is our VEB, that is the battery or the potential source across the junction emitter and base, that is our first junction. Similarly, to make the output side, that is base and collector terminal, in reverse biasing, we have to place a source here, and the n-type collector is connected with the positive terminal of the source, and the p-type base is connected with the negative terminal of the source. And let us consider this is our VCB, and to find out, measure the current in the output side as well as in the input side, let us consider we have the ammeter to measure the collector current, and we have an again ammeter to measure the emitter current in series. Hence, now we have two representation, one is our circuit diagram and another is our block diagram. Now we will deal with the common base transistor characteristic, and first characteristic is our input characteristic in common base transistor. In input characteristic, we study input voltage versus the input current, so that no other factor affects the input current. But in our case, this is our input current and this is our input voltage. We know that if we increase the input voltage, the input current will increase, because this side will behave like a forward bias diode, and in case of forward bias diode, we know that what type of graph we will obtain. But if the output voltage, that is VCB, is continuously changing, it can make our ammeter current to change. As I see this terminal, that is collector terminal, is positively potentialized, these will attract a large number of electrons, and due to the increase in the speed of the electrons, the ammeter current will increase. Hence, there are two factors which are influencing the input current. One is our input voltage and another is our output voltage. To study the input characteristic, that is the graph in between input voltage and input current, we will make output voltage constant so that it will not affect the input current. We are making our output voltage constant. Our input voltage is VEB, our input current is IE, and output voltage is VCB. It means input characteristic of common base transistor is nothing, it is a graph in between input voltage, that is emitter base voltage, and the emitter current when the collector base voltage, that is output voltage, remains the constant. We will draw a graph in between the applied voltage, that is VEB in volts, and the current, emitter current, in milliamperes. When there is no input voltage, there is no input current, because this region is behaving like a forward biased PN junction diode. If in this case we are considering that we are taking VCB as 2 volt, if we are taking VCB as 2 volt, then VB will be taken as negative, but we are considering our forward biasing potential as positive, then we have to consider our reverse biasing voltage as negative. Now if we are taking VCB as 2 volt, we have to put a negative sign, and this negative sign shows that the output voltage providing the reverse biasing to our terminal. We very well know that this is the forward biasing graph for a PN junction diode, and let us consider this is the graph obtained at minus 2 volt, and at a particular voltage the graph after which shows a increase at this particular voltage is known as knee voltage, and knee voltage depends upon the type of the base or type of the wafer which is transistor made up of. If it is made up of silicon, then this knee voltage is of 0.7 volt, and if it is made up of germanium, it is of 0.3 volt. Now if we increase the reverse biasing voltage from minus 2 volt to minus 4 volt, what will happen? We are increasing this potential. If this potential is going to increase, it will attract the electrons with large force, and due to the increase in the motion of the electrons, the emitter current will show a sharp increase at a low voltage, and we will find out that at minus 4 volt for VCB we will have a more steeper graph as compared to the graph obtained at minus 2 volt VCB. If the voltage of the output terminal goes on increasing, we are making this voltage 6 volt, then this potential is going to again further increase in the kinetic energy of these electrons, and due to which the current shows a sharp increase at a low voltage. It means we are changing the graph steeper to steeper by changing the output voltage. This change is not very large, these changes are very small, even we cannot neglect these changes. This is our input characteristic of common base transistor configuration. Now we will discuss about the output characteristic of our common base transistor configuration. In our output characteristic, we will discuss the output voltage with output current, in which the output voltage and the output current does not be affected by any another physical quantity. But in our case, if we increase the number of electrons in the emitter region, they are going in the collector region, it can increase the collector current. It means the output current, that is the collector current, can be changed by changing our input current, that is our emitter current. Hence, to avoid the effect of our emitter current or input side in output characteristic, that is the graph in between output voltage and output current, we have to take our input current constant, and in our case the input current is our emitter current, the output current is our collector current, and the output voltage is our VCB voltage, that is the voltage across the collector region and the base region. Now we will deal with the output characteristic of the common base configuration. It is a graph in between the output voltage in volts and the collector current. It is again in milliamperes, because we well know that IC is approximately equal to the IE, that is emitter current, is approximately equal to the collector current. Let us consider IE is taken as 5 milliampere, that is a constant quantity. When VCB is taken 0, it means we are taking VCB as 0 and emitter current, that is input current, is 5 milliampere. Let us see what happens in the block diagram. We are taking this potential as 0 and this side is 5 milliampere. Let us consider this as lot of electrons. We very well know that due to the forward biasing, because I is due to this biasing, if this is if I is there, it means we have given the forward biasing to the input side. These electrons will easily diffuse in the collector region and constitute a collector current. It means even when this voltage is 0, due to this biasing, electrons will easily diffuse in the collector space and we will have a small current. We will have a current which is approximately equal to 5 milliampere in our case. Let us consider this is 4.9 milliampere or 4.98 milliampere. It should be less than the emitter current. As we further increase our output voltage, if we are increasing this output voltage, the speed of the electrons will increase and it will increase the IC, and we will have a small increasing curve here. But on further increase of the output voltage, it means this terminal is going to be more positive. These electrons number is not going to change because IE is taken as constant. It means if there are 100 electrons and 5 electrons are recombining in this region, 95 electrons are approaching in this region, even this potential may be small or large, only 95 electrons are responsible for the collector current. It means on further increase of the voltage, there is none further increase in the collector current. Similarly, if we make our ampere current 10 milliampere, then what will happen? We will have an IC current. Let us now consider there are 200 electrons and these electrons are pushed by this source, and this source easily diffuse these electrons in the collector region, and there is a collector current even when there is no potential at that side. It means we will have some 9 milliampere of current, and if we further increase the voltage, we are making this voltage potential terminal positive, the speed of the electrons will increase, but out of 200, let us consider 194, 196 electrons are approaching in this region. We are not increasing the number of electrons further, and hence there is a small increase due to the increase in the kinetic energy of the electrons moving from emitter to the collector region. After the further increase in the VCB, there is no increase in the number of electrons, hence the collector current remains same, which is approximately equal to the emitter current. Now, what will happen if we are taking our emitter current is equal to 0? If we are taking our emitter current is 0, it means we have no electrons in this region, or these electrons are not further going to move in this region. It means this is 0 if I is equal to 0. But we are applying here the forward biasing, and in the output we are applying the reverse biasing, and due to this the base and collector terminal become reverse biased, and due to some holes in the collector region and few electrons in the base region. These are the holes and electrons which are produced at room temperature in semiconductors when the covalent bonds in between the silicon atoms break. These holes in the n region and these electrons in the p region are the minority charge carriers, and due to the flow of these minority charge carriers there is a flow of current in this loop. It means there is some collector current even we have no emitter current. It means when there is no emitter current, there is some collector current in this region, and this collector current nothing, it is due to the leakage current, and it is due to the minority charge carriers in the base region and in the collector region. This leakage current in our case is represented by ICBO, or it is sometimes represented by ICO. It means it is a leakage current from collector to base region when the emitter terminal is open. It means emitter terminal is providing no current, no electron to the collector and base region. It is also represented by ICO, that is, it is the leakage current when the emitter terminal is open. Hence, this region is known as cutoff region, because below the I is equal to 0, we will have IE is equal to negative. If IE is equal to negative, it means the current is moving in opposite direction, and it is only possible when the battery is connected in the opposite direction. It means this side for this region becomes the reverse biased. It means in this region output is reverse biased as well as the input is reverse biased. Hence, this region is known as cutoff region, where both sides, the input side and the output side, both are reverse biased. We seeing that the collector current is not equal to 0, even the output voltage at the certain points is 0. If we make this output voltage negative, we will move in the second quadrant of the graph, and we know that at particular points this collector current becomes equal to 0 in the opposite direction of our output battery. If this terminal, this potential is representing the reverse biasing, it means this potential is showing the forward biasing. It means this is the forward biasing of the output side, and input side is already forward biased. In this particular region, both the input and both the output regions are forward biased, and hence this region is known as saturation region. It is the region in which both terminals, input side and output side, both behave like forward biasing, and in this region both are in reverse biasing. Hence, this is the normal mode or active region of our transistor in which it is going to be a function. As our input side is forward biased, and when we obtain the forward biasing graph or input side graph, we know that at very small voltage, that is 0.7 volt and 0.3 volt, we have a large current, and we know that when the current is large and voltage applied is small, it means the resistance is small. In the input side of our common base transistor, the resistance, input resistance is very small, that is, it is the ratio of VEB, that is the voltage across the emitter base terminal and the emitter current when VCB remains constant. To define the input resistance of common base configuration, we will define as it is a ratio of emitter base voltage to the emitter current when VCB, that is the output voltage, remains constant, and it is very small because the graph is showing large increase of current at very small voltages. On the other hand, if we find out the resistance at these particular parts of the graph, we are finding out that voltage is increasing but the current is not increasing. It means the change in the current is very small and the change in the voltage is very large, hence the output voltage is very large in this case. And we will define the output voltage mathematically here, that it is the ratio of voltage across collector base junction to the current across the collector when the input current, that is the emitter current, remains constant. Hence, this is our common base configuration, and in our common base configuration, the ratio of the output current, that is collector current, and the input current, that is our emitter current, is represented by alpha, and this particular value, that is the ratio of output current to the emitter current, is known as current gain. And in common base configuration, as you know, IC is approximately equal to IE, but as it is small than IE, the alpha comes out to be 0.95 to 0.99, because out of 100 electrons, 4 or 5 electrons are going to recombine in the base region to provide the base current. To make it increase the value of alpha, we can increase the value of alpha 2.95, 2.99 by narrowing the base region and by decreasing the doping. If we decrease the doping, the number of electrons undergo recombination will decrease, and out of 100 electrons, 98 or 97 electrons will move towards the collector region. And if we make narrow this region, they can easily diffuse in this collector region from emitter region without with small chances of recombination.